Hi, I'm Reverend Greg and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. In this video we'll introduce fragment distortion shaders. This means we're distorting an image without moving the vertices. Take this image as an example. And this is what we'll end up with in this tutorial. It's just a simple image of a greenish metal plate wall, but by changing some uniforms the shader renders the image so it looks like the inside of a tunnel. Now mind, this is no three-dimensional object, it's still a plane like every sprite or surface is. But as always, a short disclaimer first.
This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths, so if you see any mistake in my video or see a better way to solve the problem, please add a comment so everyone can learn from you.
Let's have a look at how fragment distortion works first before looking into that specific tunnel distortion shader. We're going to distort this picture. To distort the fragments, we'll have to change the texture coordinates inside the fragment shader and take a sample from those new coordinates. In this example, we'll just set the sample's x-coordinate to half of VV-text chord x. So at the texture's x-coordinate 1, the new coordinate will thus be halved to 0.5. At the texture x-coordinate 0.6, the new x-coordinate will be reduced to 0.3. And at the texture x-coordinate 0, the new x-coordinate will stay at 0. Just think of what this actually means. When the GPU is drawing the fragments on the far right edge of the image, it normally would take the color sample at the texture x-coordinate 1.0. But with this shader we force the GPU to take the sample at the new x-coordinate 0.5. So the fragments on the right edge get the color from the center. And when the GPU is drawing the fragments at the texture x-coordinate 0.6, it now takes the samples from the new x-coordinate 0.3 instead. This also means the GPU will never take samples on the right half of this image. It will only take samples on the left half. And therefore the result would be the left half of the image stretched by factor 2. The main thing I want to show with this example is that if we squash the texture coordinates by factor 0.5, the result won't be squashed, it will be stretched by 1 over 0.5 or 2 instead. This is kinda like if you'd record your voice at double speed and play it back at normal speed.
It would sound like speaking at half speed.
But let's do a second example. This time we're halving the texture y-coordinate and then add 0.25. So when the GPU wants to take a sample at the texture's y-coordinate 0, it will take a sample at the new y-coordinate 0 times 0.5 plus 0.25, so at 0.25 instead. And when the GPU tries to get a sample at the texture y-coordinate 1, it will take a sample at 1 times 0.5 plus 0.25, so at 0.75. But the center, however, will stay the same. 0.5 times 0.5 plus 0.25 still is 0.5. This means the GPU can never take a sample at y-coordinates lower than 0.25 or larger than 0.75, because it will only take samples in between. And of course the result then is stretched again, but this time stretched from the central horizontal line. But on to the final example. This is going to be slightly more complicated, but not by too much. Here we're not multiplying the x-coordinate, we're shifting it instead. We're shifting it by a sinus calculated from the texture's y-coordinate. The shifting part is less complicated than it looks like. To keep it dynamic, I multiplied the texture's y-coordinates by a full circle in radians, which is approximately 6.28, and by a wavelength factor, added a phase shift before calculating the sinus, and then multiplied the result with an amplitude factor. The result will alternate between negative and positive numbers, and when added to the texture's x-coordinate, this will shift the new x-coordinate to the left or right in a sinus wave like seen in the blue dashed line on the photo. And the result would look something like this. By the way, the reason why there's no color bleeding on the left and right side of the result is because I used the surface to do this instead of a sprite. We could instead also distort the texture's y-coordinates. The calculation is the same with just all x's and y's flipped. Then the y-coordinates get shifted according to the blue dashed horizontal line, and the result would be a wave along the x-axis. And if we would combine both, it will look like this. The result is now distorted in both the x and y-axis. And this is what it looks like with the phase animated over time, where the phase shift of the y-coordinate is moving, I think, 5 times as fast as the phase shift of the x-coordinate. There's a link to the project file with all shaders up to this tutorial in the description below. One shader, object and room, is called Distort Example, and those assets show the shader I used to create this example image. I thought I'd just leave it in the project in case anyone wants to have a look at the code. Now that we got a basic understanding of fragment distortion, it's time to look at the tunnel distortion this video is about. Well, the main purpose actually is explaining how to distort fragments, but I guess the tunnel distortion was the clickbait. Anyways, if you're looking for a tutorial on this effect, you might find something like this. Distance of the current fragment to the center of the texture is 0.5 minus the texture coordinates. So the distance of the fragment's x-coordinate left to right will range from positive 0.5 to negative 0.5, and the distance of the fragment's y-coordinate top to bottom will range from positive 0.5 to negative 0.5 as well. Notice that because we subtract VV chord from 0.5 and not the other way around, the distance of a fragment left or above the center is positive, and the distance of a fragment right or below the center is negative. So I've flipped the signs here already, and signs will be very important and really tricky throughout this video. But of course the coordinate system of the texture stays normal though. Top left still is 00 and bottom right still is 11. So the new x-coordinate is the y distance squared times the x distance times a deformation strength factor, and all this added to the texture's x-coordinate. So we're shifting vv_text_chord.x. The y distance squared will create a squared curve with always positive results. Those green lines represent new chord.x at vv_text_chord.x 0, 0.25, 0.5, 0.75, and actually 1, but at the moment that line is off the texture. Times distance x will flatten the curve the closer x gets to the center of the image, and due to the negative sign, flip it on the right side. And the deformation strength will scale the curve. The same as in the previous examples applies here as well. If the x-coordinates are squashed, then the result will look stretched. Imagine you stretch the top and bottom of those green lines in the direction of the white arrows towards the edges, and you can see how that will stretch the image. The green lines closer to the center will deform the image still, but not by as much, and the green line at the center won't deform the image at all. And that's what it looks like. But I don't like the result. Looking at this causes headache, and I think that's for two reasons really. Reason one is the shape of any squared curve. It flattens towards the top and bottom and makes this tunnel look oval shape instead of round. So we'll need to find a better curve. And reason two is that the focus length seems unnatural. Since we're only deforming along the x-axis and not changing the y-coordinates at all, the metal plate tile's height of this tunnel wall don't change. So the tile height should be decreased towards the top and the bottom and increased at the center. It actually also depends on distance, but to me it just looks wrong. Those two reasons sound like they're the same, but they're not, as you'll see. But anyways, I tried to figure out another algorithm and we'll look into it in a bit. Just keep in mind I'm no maths crack and there are most likely better ways to do this, like actually calculating a perspective projection. But if you know ways to improve my code, pretty please tell us in the comments. It really would be appreciated. But before fixing these issues, let's have a look at the project and implement the squared curve version as a starting point. Unlike in previous videos, I don't want to spend as much time editing a video where you can watch me typing and all. Instead, I'll just code off camera and talk you through the finished code. Also, I don't plan to explain how to implement sliders and how to deal with my GUI system. I already did that many times and it starts to get boring, to be honest. So I'll reduce the time spent on that as well. I hope most of you won't mind. So this is the project file with all shaders coded in all the videos in this series so far. In here you'll find the example with the wobbling droids from earlier. Sprite, shader, object, and room. They're all called distortion example, just in case you want to have a look at the code. But in this video, we're mainly looking into the assets named tunnel distortion. I added the tunnel distortion background sprite, a tunnel distortion shader, an object which started off as a duplicate of the base project's object module template, and the tunnel distortion room here. Inside the room I killed all the toggles and triggers since we won't need them. For some reason I have a hard time to just delete them, but you can. And I added 4 sliders. Just remember, if you're adding sliders yourself, move them up in the creation order to where the other sliders are, or they won't work. And of course I added the test module object called Object Tunnel Distortion. Now let's have a closer look at the object. In Create Event, I already described the module in the title region. In the sprite and shader region I set the tunnel background sprite, and later I'll draw the sprite tiled to surface, and for that I declared a drawing offset x and y and a surface variable. Then I also declared the shader and created a uniform handle for the deformation. Now beneath that I got a region to set up the sliders. The first 2 will determine to how fast the background moves across the surface, and I just named them y speed and x speed. The next 3 sliders will set the deformation, and I named them deform x, y and size. I set standard values and set the wider button sprite. and the last 4 sliders are just for a simple lighting effect to add some depth. Not so important for this video though. First thing in Draw Event is I'll change the tunnel offsets. Depending on the 2 first sliders, these 2 offsets will increase or decrease by -5 or +5 pixels per frame. You'll see how in a second. And I'll also grab the deform X amount from the 3rd slider. This will function as a deformation strength factor we've seen on the slides from before. Then I'm creating the surface if it doesn't exist yet and draw the tunnel background sprite onto the surface. In this demo project I'm just drawing the sprite tiled with the offsets we calculated a second ago, but in a real game you'd probably create and draw upon this surface in another object, like in example drawing a background layer or tileset layer on it. And the offsets would probably depend on the player's position in the room instead of on a slider. Once we got the surface though, we can finally draw it distorted. I'll use the linear texture filter here because without it we'd get some pretty nasty flickering. Then I'll set the shader, pass in the uniform deform X, draw the surface, reset the shader and turn off the linear texture filtering again. Of course if your game uses the filter anyways you could remove both those lines. Now the shader. The Vertex shader is just a simple pass-through shader. We won't even need the Vertex color, so I even removed VV color and in color. Inside the Fragment shader we can grab the only uniform and then calculate the distortion in the main function. First we'll need the fragment's distance to the center. Then the shift amount for each sample is what we've already seen before. Vertical distance of the fragment to the center squared times the horizontal distance times a constant and a dynamic deform factor. Since dist y is squared, its sign won't matter and only the sign of dist x will flip the direction of the distortion. Then we can finally grab the color at VV text chord, shift it in the x-axis by the deformation we just calculated, and that's it. This is pretty simple, but let's run this and have a look at it. So it does look like a tunnel already. It actually does look pretty much like the Castlevania IV spinning tunnel, but as mentioned before I don't like the distortion. It never really looks around with this function. The top and bottom regions look too flat and it lacks some squashing on the top and bottom as well. Now let's take care of the first problem, the shape of the curve. I'll show this in Desmos and leave a link in the description of this video. Imagine the grey area being a cross-section of the tunnel. To the right somewhere is the observer. The black line represents the rear wall of the tunnel. Now with the squared curve from the previous examples, the tunnel's shape would be something like the red dotted line, and now we can see why the example looked flat in the upper and lower sections of the tunnel wall. So we need to find another function to distort with. Now this is an interesting function I found. The square root of 1 minus x squared is a half circle. All we need to do is make this fit into that grey square cross-section of the tunnel and make it face towards the observer. The number 1 in there is a scale factor. Reducing it to 0.25 will reduce the radius from 1 to 0.5, and that fixes the size of the circle. And since we want a new x-coordinate, we can flip all x's and y's, so now it's a function of y instead of a function of x. Multiplying by -1 mirrors the shape across the y-axis. Subtracting the radius from y shifts the shape up. Adding the radius to x shifts the shape to the right into the cross-section, and now this looks much more like a tunnel than the squared curve. We'll build pretty much everything around this curve, and for the rest of the tutorial I'll just call it the distortion curve. And this is a more dynamic version of the distortion curve. Y is replaced by text chord y times a y scale factor. We're going to send that factor into the shader as a uniform. The first 0.5 was shifting in the y-axis and is now replaced by y-shift, which is just y-scale times 0.5 to keep the curve inside the grey area when scaling. The whole square root is multiplied by a x-scale factor. Again, we're going to send that factor into the shader as a uniform. And the second 0.5 is replaced by a x-shift, and here again x-shift is just x-scale times 0.5 to keep the curve inside the grey area. Now let's change the perception a bit. So far we looked at the grey area being the cross-section of the tunnel. From now on, let's look at this being the surface with the tunnel wall image we want to distort. The black line is no longer the tunnel back wall, but rather the distortion line where we take samples from when vvtextchord.x is 0. As in the squared version, we can now calculate the distortion curve for any texture coordinate. We'll just multiply the distortion curve by 2 times dist x. so the distortion decreases towards the center and flips at the right side, and then add that to text chord X. X-scale scales the distortion curve down in the X-axis, and this will basically look like increasing the tunnel size. Y-scale scales the distortion curve up along the Y-axis, and this will look like changing the focus length. Scaling it down by too much will look too distorted though. And this is about a reasonable combination of the scale settings. Just as a quick reminder here, we're squeezing the X-coordinates towards the central vertical line. This means the result will be stretched. The bigger the shift, the bigger the stretch. So the top and bottom will be stretched the most, and the center in both axes won't stretch at all. Now back to our project. I already implemented the new code, and I'm going to show what changed. Now nothing changed in CreateEvent. We still only need one uniform handle. We'll just pass in multiple values through this handle. In DrawEvent, I added a new local variable, deform size, and set it to the 5th slider. And I'm passing that new variable to the uniform deform as well. Inside the fragment shader, the uniform deform now is a vec2 instead of a float. The first component will be referred to as deform X, but it would be misleading to refer to the second and new component as deform Y. So for better readability, I defined a macro named deform size to replace deform Y. The main function has changed completely really. First I defined a few variables needed. This will be the same as before, the fragment's distance to the center where top and left are positive and bottom and right are negative. And distortion is the formula which is created in desmos. Here we'll use a different naming though. The Y in desmos is replaced by vvtextchord.y, and the Y scale in desmos is replaced by deform X. Changing this value will have the most effect on the deformation along the X-axis. And the X scale in desmos is replaced by deform size. Changing this will mostly change the perception of the tunnel size. So with this line we're calculating the distortion curve. Now we need to calculate the shift amount in the X-axis from this distortion curve. Now we know how much we need to shift vvtextchord X to get the sample's X coordinate. And that's it. The output is the same as before. The fragments caller at vvtextchord shifted in the X-axis by sample X shift. Now let's run this again. Moving the deform X slider shows how it affects the deformation strength. And moving the deform size slider shows how it in or decreases the tunnel size. Mind it only changes the curve and not the texture size. You'd have to change the texture size in the draw event when drawing the texture to the surface, but of course you could tie that scale factor to the same slider. Now we need to tackle the second problem. I still don't like the fact that the top and bottom sections are as high as the center section. So this is how our tunnel's Y-axis is segmented at the moment. There's no stretching and squashing at all. And this is what I want it to be. Everything should be shifted towards the top and the bottom. The tricky part is by how much. To see more clearly what the difference is, we can connect the lines. As you can see, they're not all shifted by the same amount. First, it's quite obvious that the center isn't shifted at all. But I also don't want to shift the top and bottom line because we cannot exceed the surface in case whatever is on the surface won't wrap around perfectly. So only the lines in between need to be changed. That was quite a challenge for me to do, but I'm kinda happy with the result. Looking at the connecting lines, we can observe that the central connecting line is horizontal. Then the lines get steeper with increasing distance from the center, but somewhere around the blue lines they start to flatten again until they reach the top or bottom line where they're horizontal again. We already know to squeeze the image we need to stretch the sample's coordinates and the other way around. So let's flip those connecting lines and draw dotted lines where we need to pick samples from to get the distortion. I know this starts to get confusing. I just didn't find a better way to graphically explain what we're doing here, but to be honest, this is pretty much how I created the formula because I was not able to do it with maths alone. And let's also flip the stretching on the X-axis to get a more accurate picture of where we're taking samples from for both the X and the Y coordinate. Now to visualize more clearly by how much we need to squeeze or stretch, I'll just extend the lines and draw the distance between the solid lines and the corresponding dotted lines. Still hard to see the relationship between the lines, so let's compare them side by side. And now we're getting somewhere. From the red center line to the top, there's a rather steep, nearly straight curve up to a maximum at the blue line, and then the curve falls off very quickly until it reaches the top white line. Now we got the information needed to create a function for this. So let's flip those bars and draw them in a coordinate system, and this time both the top and the bottom half of the image. Obviously we'll need to combine two curves to get that shape, and I've picked two we already got. And the first one is the distortion line we used in the last step already. But as it is right now, it won't help us, so let's flip it along the y-axis. We can do that by calculating the maximum possible distortion with the current deform factors. Remember that was y-scale and x-scale in desmos, and then subtract the distortion from the maximum distortion. That's kind of like inverting a percentage. 20% inverted would be 80% because 100, the maximum, minus 20 is 80. So the shift amount along the y-axis would be max distortion minus distortion. But we're not there yet, the shape doesn't fit yet. So let's use another line we already got, dist.y. Dist.y is 0 at the center and linearly increases towards the top and decreases towards the bottom. And multiplying those two lines would look something like this. Note I also multiply by a deform factor. That's going to be a value passed into the shader and will allow us to dynamically change the distortion. Not quite done yet though. If we'd stop here, we'll stretch and squeeze the y-axis only. To compensate the deformation on the x-axis, we'll also need to apply this formula there by adding it to the x shift we already had calculated before. And instead of this y, we'll use this x here. Now we're done. A complicated explanation for two simple lines of code, but as mentioned I didn't find an easier way to show what I was thinking when creating the shader. But now it's time to show the code and see what the result looks like. The create event remains unchanged. We'll still only need the deform uniform handle to pass everything into the shader. In draw event I added the local variable deform y. This will be the deform factor for the distortion along the y-axis. And I also added the local var max distortion. As a reminder, here's the code we wrote in the fragment shader. We know the distortion is at its maximum when vvtextchord.y is either 0 or 1. This means the function of max distortion is the same as the function in the fragment shader, but without vvtextchord.y times deform x. Previously we already set the uniform deform x and deform size. Now we also need to set the two new variables, so deform x, deform y, deform size, and max distortion. But that's all for the draw event. In the fragment shader, the uniform deform now needs to be a vec4 to receive all four variables. The macro deform size now needs to replace deform z instead of deform y, since deform size now is the third component of the uniform. And for better readability, I also added another macro. It's easier to understand max distortion than deform w. Inside the main function, I changed the variable definitions a bit. Distortion still is a float. But since we now shift the x and y coordinate, I turned float sample x shift into a vec2 sample shift. I also added a new float deform y fixed, which we'll use in a sec, but vec2 dist remains unchanged. Also the calculation of dist and distortion didn't change at all. The calculation for the x shift stays the same as well. I'm now just using the new vec2 sample shift instead of the previous float sample x shift. And here's the code for the y distortion. Deform y fixed is the inverted distortion times the deform factor. Sample shift.y is deform y fixed times dist y. And sample shift.x gets corrected by deform y fixed times dist x. And now the output line got a little bit simpler. We'll now pick a sample at vvtextchord shifted by sample shift. So let's run this. I've set up some pretty extreme values here. And the x deformation is 0.9 and deform size is 1, so a very much stretched small tunnel. Now focus on the top and bottom segments and you probably get a headache pretty quickly. At least to me it feels very much off without the y deformation. Now when I increase the y deformation, the middle segments will scale up and the top and bottom segments will scale down, and that fixes the perspective. Now I can change y speed as much as I want without getting a headache. So much better. Of course, the fact that the middle segment gets scaled might be a problem for your game. This means the artist might need to create smaller assets just for this effect to look proportionally correct, but that's the price to pay to make this look good. Now as a quick bonus, I'll add some pseudo lighting to add some depth. Mind, it's probably not the best and optimized way, and I won't explain everything in detail. In create event, I added 4 uniform handles for the light's core size, the light's gradient or fall-off size, the light's position, and the overlay strength. And in Draw Event, I'll grab the last 4 sliders and pass them to the shader with the new uniform handles. Inside the fragment shader, I grabbed those new light uniforms, and inside the main function, I defined a new vec4 base call. Then instead of setting glFrag caller to the sample caller, I first set base call to the sample caller, because we're going to change the sample caller according to the pseudo lighting. Then I'll define some more variables needed to create a gradient and the blend caller. And after that, I'm creating a gradient, and that's the part I think could be done more elegantly. First, I'm creating a smooth stepped gradient above the light's position. If VV_y is smaller than the light's position minus half the light's core minus the gradient size, gradient 1 will be 0. And if VV_y is larger than the light's position minus half the light's core size, then gradient 1 will be 1. And everything in between will be a smooth stepped value. Then I'll do the same flipped for the gradient below the light's position. After that, I'm stitching the gradients together. If VV_y is smaller than the light's position, we want gradient 1, and if not, we want gradient 2. And finally, I don't want any black, so I'm shifting the gradient to range from a dark 0.3 grey to white. Now we can overlay like we did in the video on the day and night cycle shader version 1.1. We get the base color value, calculate the overlay color, and mix that with the base color according to the overlay strength uniform. And all that's left is setting glFrag color to base color. Now we got a light, we can set the core size, the gradient size, the position, and the overlay strength. So that's it for this video. We learned how fragment distortion works and created our first math-based distortion shader. I hope you're now able to create your own algorithms like waves, swirls, or whatever you want. I think the code itself is rather easy. As usual with shaders, the maths is the major difficulty. In one of the coming videos I plan to add some texture-based distortions, but I haven't decided on the details yet, haven't coded one yet, so let's see how much time it takes to learn that stuff, create something pretty, and then create a video. I hope you enjoyed this series so far. Until next time.